first time. All right, so my name is Kevin Goetsch. I started the data science team at Braintree about a year ago. Braintree, as you heard, is a payments processor company. We do some science on that. My background is in machine learning. I graduated from DePaul with a master's in economics and policy analysis. I went to Allstate, did a lot of predictive modeling there, and now I'm here to kind of give a talk. Data science is hard. Tuning machine learning is hard. There are a ton of free tools that make it way easier. So I'm going to focus in on a single tool to kind of make tuning a machine learning model of some sort a little bit more approachable, a little bit easier to use, so that there really isn't an intimidation factor. So data science, what is it? It's got a lot of media. Broadly, it's applying predictive models. So you apply to Braintree to be a merchant. Maybe you're trying to scam other people. Maybe you're not. How do we tell? We can use some machine learning to figure out who was fraudster, or sorry, we know who were fraudsters in the past, so we try and predict who will be fraudsters based on that past information. Very simple. This would be called like a classification. You could use a logistic regression. You could use something crazy complicated. What you use is kind of part of the process. So data science, a lot of steps. They're very complicated. Examples of these steps and kind of the flow of the process. You collect some data. You do some cleaning. So maybe you get a credit report, right? Maybe you roll up to a merchant level. Feature creation. Maybe you create a dummy variable for whether or not someone's under 21. You select different models, classification versus regression. I could go into each and all of these. I don't want to. It's very complicated, but not impossible. It's very easy if you just kind of go through it step by step. We're going to talk about just model tuning today. So we've gotten data. We've created some features. We've selected a model or two, and we're going to tune the parameters around that model. Everyone with me? We good? Everyone's awake. All right. Two main things we do to tune a model. We use cross-validation, which I'll explain, and then we'll talk about actually doing a grid search across the parameter space. So, cross-validation. We have data, some amount, hopefully more than less. If you just train a model on this data and then predict on this data, you should be pretty damn accurate. Because you've just trained on what you're predicting on, this is called overfitting, very common problem. So you want to have a test set. So maybe you hold out the last 6 months of data and train on everything before that, and then predict on that remaining holdout set, which is great, except sometimes time actually matters. Like maybe there was a recession, or maybe you went public, or any of this kind of crap. So maybe you just randomly pick a slice, but maybe that also is time-based. So maybe you pick a bunch of tiny slices, this kind of thing. You just randomly pick it. The point is you're trying to not get caught up in any single bit. This is not fully cross-validation yet. This is just like train, test, split. I can take questions in the midst if people have anything. Have I lost anyone entirely? No one brave enough to wave their hand, at least. All right. So then we score it. So you've trained a model. You've now scored your model on this holdout set. When I say score, there's a number of different things. There's words like precision, accuracy, recall. I'm just going to talk about accuracy, which is like the total number I got right over the total number of actual instances of the thing. So I predicted correctly 80 merchants out of 100. That would be a 0.8, right? Or in this case, a 0.87, 87 out of 100. So a perfect 1, I predicted everything awesome. A 0, I was worse than just guessing fraud for everyone. So that's our score. We're kind of using it as a metric to compare models. There are a ton of subtleties about whether or not you use score or recall or these kind of things. We're just going to use score for right now. It's simple. It gets the point across. Because, as we saw, we can actually do it multiple times, right? And if we do it multiple times, we might get multiple scores. So different ones. One has a single score. Bam. Now we have 3 different scores. This is called k-folds. Like the parameter for how many times you do cross-validation is a k-fold. K as in any number of numbers. So 3 is a number. 7 k-folds is nice. You're really only kind of constrained by processing power. Because the more you have, the more you're sure that you're not overfitting if you have a significant test holdout. So you have scores from all of them. You just take the average across all of these. Now we have a model. We've ran cross-validation. We have a pretty good idea of what it looks like. Cool? I'm going to go on to parameters, grid space. I have no idea my time. Oh, I am flying. But does anyone have any questions? Because we're going to come back. Yeah. The question is, does the k-folds cross-validation actually affect the model or only verify that it works? It's building confidence that your model is not giving you some erroneous result just because you've held out a weird slice of data. And this happens. There is data with big outliers, and if perhaps you don't include this tiny 3% of your data slice that happens to include all of the, I don't know, homes that you're modeling over $1 million, suddenly your model does not apply at all. So you'd like to have those kind of interspersed a little bit. And the best way, because you don't want to do something where you're manually picking, oh, this needs to be in here and here, because then you've lost all the science. You're just kind of manually doing things, is to just do it randomly, a bunch. And statistically, you're just going to get this nice spread. When you do this, you can look at just the average output. You can also look at the individual scores from each of the k-folds. And if there's a huge variation, that signals that something's funky. That's where I would start diving into the data, see if we actually transcribe something wrong in one of those earlier steps. We're talking about data cleaning or feature creation. Yeah, and that happens. That happens a lot, where maybe you didn't know that your data was duplicated, and so you've actually rescored the same merchant 30 times because your data is maybe just every time they change something in the system, not every time they applied. This is the kind of thing that you're trying to catch signal for, both signal as statistically for machine learning, but also signal of maybe my data is a little wonky. What are my instincts telling me? It's kind of a weird line. I'm definitely not a scientist, despite the job title. It's definitely a little bit of art, a little bit of just experience and guesses. And then you're using this to really confirm that you are actually confident with where you're at. Any other questions? That's a good question. I mean, this talk's going to be done in 5 minutes if I don't get some good questions, so I'll slow down a bit. Model tuning. There are a lot of parameters in predictive models. Which ones do you tune? What do you leave at a default? What is even model tuning? We will try and cover a lot of that. There's cost benefits to a lot of this. Some of it is that you can tweak parameters that have no effect in your use case, and you've just wasted a ton of processing time. Sometimes you can overfit or fool yourself by tweaking the wrong parameters. Other times you can really miss a ton of value by not tweaking a parameter. Yeah, I don't know how to explain it besides it's kind of like building a car. I don't expect people to intuitively just know how to do it. You need to be experimental. You need to walk through it, especially with a new technique. You need to do some reading. It takes time and experience, and it's really cool when you're I could just change this one thing and just tons of value appear. So, scikit-learn random forest. How many people know what a random forest is? A lot of hands. How many people feel comfortable tuning all the parameters in a random forest? No hands. 2 hands. Yeah, all right, some brave folks. I don't feel comfortable tuning all of them, but I feel pretty good on most of them. We're going to look at scikit-learn. This is the code. N estimators, criterion, max depth. The names are not the most intuitive. The names don't tell you a ton unless you're already in the paradigm of understanding what they're referring to. Normally when you talk about a random forest, you might talk about the number of trees involved. N estimators is what it means by trees. Why it's not called trees? There's good reasons, but in the context of you learned what a random forest is and it has multiple trees. Oh, I should have gone back to the people who didn't know it. We're going to, take a step back. How many people who don't know what a random forest is have an idea of a decision tree? Huh? All right, cool. So it's just little branching, and maybe where it branches, so maybe the Titanic is the classic example. Who survived the Titanic? Over 21, under 21, right? It just splits them up. And suddenly, where you had, I'm going to make up numbers, a 50-50 chance of survival, which you did not, suddenly the over 21 and under 21 have different percentage chances. So you know if they fit into one of these categories, suddenly they're more likely or less likely to have survived. Decision trees. Now, over 21, under 21, over 35, how many branches do you have? And let's say you only have 2 people under the age of 2 in this made-up example. Do you actually create a branch for them? That seems insane. How are you going to model beyond that? So these are things where you set how many minimum samples do you need to split? How many nodes will you split on? That sort of thing. Decision tree. Random forest is, okay, we got one. Let's do another one and another one. And like cross-validation, let's do a couple thousand of them and just average the results for any given person. So myself, I go here, here, here in this tree, and here, 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 and this gave me a 75% chance, this gave me a 60, and we just average the results. That's how we're doing classification. Random forest, broad strokes. I didn't prepare any slides on it. These names here, bootstrap, OOB, score. Scikit-learn docs explain some of it, but a lot of it is you have to be already knowledgeable and know what you're looking for. which can be frustrating, as I have found. So yeah, what do we find for the optimal number of trees? The max depth, the min sample split? I know, like most of these, I couldn't really give you a difference between min, weight, fraction, leaf. Yeah, I just have never tweaked it. Maybe I should. I like to do min number of samples and tweak that. And it's also compared to your data. So the big thing with grid search is, which we're about to get to, you can do a whole ton of different machine learning cross-validations, but if you don't even know what kind of area you're in, if you just do every single thing, you might get to a lot of local minima that are totally misleading, right? Because you can tweak these parameters so far out of whack with each other that you're just going to get totally bonkers results. And even if the score says it's the best, it might not actually apply to your real data. So a little bit of reading, a little bit of experimentation. I'm kind of just saying throw everything in the stew pot and, yeah, experiment. That's the big key. Any other questions? Yeah. It is. So the question is, isn't cross-validation supposed to make sure you're not throwing things out of whack? Definitely helpful, but if you don't know your parameter space or your data space, I just had a problem at Braintree where, turns out, for good news, we don't have a ton of fraudulent merchants. So if I'm trying to accurately model who's going to be fraudulent, if I guess no one's fraudulent, I'm like 89% accurate. That is awesome. On the other hand, maybe I don't actually care about accuracy as much as like, maybe I care about the number of false negatives, where we just want to minimize that number no matter how many false positives we get. So the score that the grid search would pop out or that a cross-validation would pop out would say, heck yeah, no one's fraud. But you actually need to tweak some of that and look at the actual results. So maybe you weight it. There's a class weights, yeah, very last one, class weights, where you say, okay, my Y is actually 10% of my data. What if I actually resampled until it was 50% of my data? So you're weighting that like Y response class. Suddenly your score is horrible, but your score from a random forest with class weights is better than your score from a logistic regression with class weights, and those are more apples to apples. Feel like I've kind of lost track of where we were going with this. Other than the fact that there are a lot of gotchas, I recommend playing across all the space, not relying on this to overly automate things. And that's, I think, a big point that I get to at the wrap-up of the talk, is that it's easy to overly automate things. It's also easy to do everything manually. I think it's intimidating to do everything manually, and I think it's just awful to do everything automated, because then you don't actually understand what's going on, and the gotchas always get you. Yeah, that's a phrase. Yeah, so let's talk about parameters. I have a parameter. I want to see a random forest that has 100 trees, right? So back to this. I've got data. I've got a score on this. But in fact, I've got cross-validation. Good. I know random forest, 100 trees, got me like at about an 87. Oh, 2 more slides. 85. There we go. Averaged across. And there's not a ton of difference between these scores, so I'm not too concerned about holdout. Neat. But now I want to know like 5,000 trees. I can do the exact same thing, right? Could do it manually. There's a tool that does it for you. They're both viable. There's reasons we use the grid search at Braintree, mostly to do with us being a tiny team, not wanting to maintain a ton of sloppy code, wanting to read each other's code, wanting to read your own code like 3 months from now. It's a nightmare if you have a bunch of nested loops, in my experience. But all of this is just built into scikit-learn's Python distribution. Yeah. Go 5,000 trees. Processing time takes forever unless you can multi-core, which I'm happy to say grid search allows you to just say use all my cores, which you can spin up, and it's awesome. The question is, did I pick the 5,000 or was that automated? I picked the 5,000. When we get into the actual grid search code, which I really did not get into heavily because I don't like looking at code during presentations, you just provide like a list, either a range that it randomly picks a certain number from, or literally like give me 10, 20, 100,000, 25,000, and it will just do them all, which I am going to get to right here, unless there are any other questions. My other talk, the question is, what influences my choice of what goes into the model? What variables? Oh, what parameters am I choosing to tune? Yeah, so the question is, what information do we ask, like a new merchant signing up, to provide in order to predict on this? We ask a nice little list of like URL, business name, average processing, and then we also pull in from third parties like credit report and inquiries. And that's all covered in like the data collection area and the data cleanup and all that. And then the real big question ends up being kind of what model do you choose? Because there's the big, like, do you do classification versus regression? And am I guessing, are you a fraudster? Or am I guessing, how much are you going to lose if you are a fraudster? Am I looking for like money or not? Does that answer your question? Or what do I use in the model itself? Yes. So do we ask, and that gets into A/B testing and model validation and some of those final steps after deployment to me. So I'm trying to focus in on the tuning, but yes, every part of the data science process is totally convoluted, and you can take weeks going back and forth between things. We have some systems that we run to be like, give me like significance of variables and sort them by p-values and that sort of stuff, which I don't really put in the model tuning as much as maybe run the model tuning multiple times on different feature sets by talking to the risk team and finding out, oh, actually they don't care about these things. All they care about is these things, and that kind of plug and play. Cool. So min sample leaves. The number of samples required to split off a leaf, if I recall correctly, and if I don't call me out. Oh, the screen's cut me off. 5, 10, 20, 50? Great. So we could do cross-validation on these, right? But what if I still want to try number of trees? We just do a Cartesian join, and this is all Gridsearch is doing. It's doing a Cartesian join of your entire parameter space. So suddenly we have a bunch of these things. And I didn't have to code this up. I didn't have to do loops. I just said, I'm interested in this feature space and this feature space. And it goes ahead and creates all this, which is wonderful, because I can get access to every bit of this nested in as much as I need, or I can just call best estimator, and it's just like, hey, that one's the best. But it gets to your point where accuracy scores are misleading in some data sets, and that kind of thing needs to be played with. So I recommend getting into the actual responses from the grid search itself. Cool. Any questions so far? I'm going to have a ton of time for questions at the end, because I talk fast. So we're going to look at some code. It's awful code. I wrote it in 15 minutes. The point is, all of this is just a nested loop, right? So we could do this all manually. It works up until the end when I kind of lost track of it, where we don't actually record which ones were best or what parameters went where. But you can see that, like, up top we have a list of parameters I want to go over. And then just nested loop after nested loop. We create this estimator object. We feed it. I do the train test split manually. So this is, yeah, I'm just going to kind of, I got time. Right here, right, we're just actually resplitting up the data to do the cross-validation. So we're splitting it randomly. That's what the train test split is, pulled out of scikit-learn, giving me 35% as a test size. Then we're plugging it into the fit. Then we're scoring on the test set. Any questions on this terrible loop that is pseudocode, and I don't guarantee to work? You see how you could do this, though, right? I mean, it's just a nested loop over a bunch of parameter space. So there's two cool things. This is the half-grand reveal, right? So this is grid search code. I wanted to provide it in the presentation so that people can start playing with it in the future. This is doing the same thing, except I'm just providing a logistic regression as my estimator object. The parameter grid is just a dictionary of different values, the C value, the penalty, the class weights. If we were to go back to that whole random forest thing, all of those things are up there. And then it's just going to do a grid search, right? So that CV equals 7, that's the number of k-faults. You can change it depending on your processing power. There's also something you can add to the grid search called njobs, where you tell it how many cores to use, which is awesome if you're doing something like a random forest with a bunch of things, because then you can just spin up as many cores as you have. You just call a fit method. So it's doing all the cross-validation. It's doing all this train test split randomly. It's doing all the averaging. It just gives you the best estimator. Or I can call grid search.estimators and get my like several thousand trees. I could get into any individual decision tree in any of these runs. Never mind, it's a logistic regression. There are no decision trees. Damn. We'll get back to that. Yeah, but had it been a random forest, the code looks basically identical, which is the other grand reveal. Here's a gradient boosting classifier. So gradient boosting decision tree classifier, really, which is a lot of words for a single model. But it's doing something similar. It has n estimators, number of trees, and the key cool thing to me is that I understand logistic regression really well. It's taught in high school, right? Like, it's very established. I was not totally familiar with gradient boosting classifiers when I started playing with them, but I'd read some good stuff on Kaggle, I followed some forums, I started playing with it, and the ability to just change up a little bit of code, change up what the parameters are, and not have to like rewrite your whole loop and change your names everywhere in which way is amazing, because it means I can just switch out a new model. I can try a new classifier at the end of my pipeline. Maybe I have a feature set that I'm like, this is really odd. Why don't I try several different things? Very simple. Not only is it simple to do, it's really easy when you have your like coworker who just did stuff and you're like, wait, what were you searching over? I am not reading that loop because, ooh, this is just a logistic, much less like, you know, a parameter space with a ton of variables. You can just go and look at this parameter grid and you're like, oh, I get it. It's easy, it's comprehensible. There's a whole other aspect to this where this thing, this grid search best estimator object that gets created after fitting is actually an object that you can take out and plug into production if your systems are set up that way. You can take this fit object and use it elsewhere. You can score it on data that was totally outside your sample, which is really cool. And I have a whole talk on that, but maybe I should have given it because I have plenty of time still. Any questions on this? Raw code is the worst. So I think you should. I think you should maybe graph the results and kind of look at where, you can also look at the scores on the training set, right? So we talked about overfitting, but if you look at the scores on the training set and the scores on the test set, and see that the scores on the training set like get way better, suddenly you know you've overfit at some point. Like if we, on our imaginary x-axis, have number of trees, 10, 20, 30, 50, 1,000, and around 50 they cross, you're like, ooh, overfitting to really just only be able to use the training set. Cross-validation helps, but yeah. In the end, like day to day, you build expertise. I think the cool thing about grid search is that you don't need to start with expertise to start playing with things. And you can start tweaking things. You can have a whole series of min sample leaves, and it never makes any difference if you look at all of these different outputs of averages of cross-validation. So you're sure you're not just like oversampling or anything. You just know they didn't actually make a difference on this data set, which is really interesting. You sound like a plant, but that's the first question. The question is there a way to just snag out the model that you want to use? Because you don't want to rewrite it and maybe grab and manually enter like another 30 different parameters, just the correct parameters that were chosen. The answer is yes, it's very easy to pull out. Grid search best estimator should literally return you an object. If it's inside of a pipeline, which you'll see on the docs, you end up doing something like pipeline.nameSteps, and then in nameSteps is a dictionary that contains all these steps. We haven't talked about pipelines. scikit-learn has some neat paradigms around pipelines and grid searches. It's very simple, and I can show you afterwards if you like how to literally get it out, but one of the things you put into grid search is refit equals true, and that means it does all of its cross-validation, and then it grabs your best one, it refits it on the whole training set, so it no longer takes a test set, so that you've actually given it all your data, and you've gotten a fit model out, and you can just grab that fit object straight out, plop it into production. That's actually kind of what we do, is we just save that fit model object into a pickled, and then our production system just grabs it out of its pickled form, which is pretty nifty, I must say. Not us, but this tool. The tool makes it easy is kind of my point. The tool also gives you access to the Cartesian join of all these parameters. It's created a new estimator for every single one of these, right? So 12, 2,500, however many estimators actually get created. It gives you access to all of them as objects in addition to their like output and scores on each individual cross-validation. So you can get pretty deep inside of like nested, nested, nested. Strongly recommend. Any other questions? The question is, do we change our models frequently enough to get a sense for how stable these search parameters tend to be over time? Do we? Yes, we change them a lot, but it tends to be feature creation and selection that tends to go back in. We just sometimes don't have data that we now get access to or that we didn't realize was important. I don't want to help any fraudsters, but we heard from our, when PayPal bought us a year ago, we heard that the number of capital letters in an email address is very predictive on some of their stuff. And we were like, I didn't even think about that. I am going to try that. And that was pretty neat. That's the kind of thing where some of that has a ton of value, some of it doesn't. But there's a lot of gotchas in feature selection and creation that I could go into. But then I would run out of time. Cool. So we talked about this a little bit, but this is kind of basically my wrap-up. Cross-validation for free is a huge benefit. You can do train test split manually. You can do all the cross-validation you want. I don't see any reason to burden myself with it when it's already here for free. If you overly automate everything, right, because you could just say, like, give me every possible feature, and then iterate through every possible feature in every single grid search and give me the output, and you'd get some optimal output, but that output could be no one's fraud. And that's where it's like, I still want to have my fingers in it deep enough that I can track and follow what's going on, which is why I like discrete steps kind of for each of those 8 big model tuning, model selection steps, that sort of thing. The parameter space, without overfitting, thanks to cross-validation, you're pretty confident in. The parameter space, this is to me really huge because not a lot of people know everything about every model, about every parameter. I certainly have no idea, and I feel much more confident being able to just plug it into, like, I know kind of what my data looks like. I know what, like, a logistic regression gives me out. When does this gradient boosting decision tree give me way better or way worse? What kind of parameter space am I in? I don't know yet. I'm just going to play at it and plot the results. Easy to pick up someone else's work or your own work is huge. I don't know how many people have ever, like, tried to pick up their own work 3 months later, but you just hate yourself. Maybe that's just me. It helps kind of enforce a consistency rather than like forcing you to kind of refigure out how to do it because suddenly there's a new parameter that you haven't used in your nested loop and you only want to use it in some cases and that sort of thing. Explore machine learning techniques and integrate smoothly with the rest of scikit-learn's kit, which to me is really huge because we use pipelines, we use transformers, and these are objects that in kind of my visual world of my hands live up here, process the data, feed it to a next step, and then feed it to this actual grid search so that this entire pipeline can be just saved, stuck in GitHub, pulled out later, examined later. Trying to keep that kind of as reproducible research is really difficult if you just have code floating around that's like _2, _final, _this one, which everyone has done at some point, I assume. Not me, though. I've never. But that's it. Any questions? More questions? Adam. Yes. So the question is, can we basically add a penalty term so that we don't overfit on just pure accuracy as opposed to like really trying to never have a fraudster even if we have a ton of false positives? There are costs and benefits. A lot of it's just time and ease of explanation. Tweaking the parameters. So even a logistic regression. Who knows what a logistic regression is? People pretty good? Sigmoid function, kind of looks like a snake. Typically, you set like a 50 cutoff, and you say anything over 50% is definitely true, under is false, and then things fall on this. But you can just move that cutoff to be more or less conservative. Right? That's a very simple kind of idea. That's in some ways easier to explain to the business user, which is also part of what this is, than trying to introduce some sort of complicated penalty term and put it into like linear optimizations and that sort of nonsense. Does that kind of answer the question? Yeah, cool. Definitely a plant.
So when you talk to the data teams of your competitors, do you all end up with a similar modeling when you predict
We just fight. No, when we talk to data teams of competitors, do we end up with similar models? Yeah. No.
Common features across all users in the industry?
hard to say. When I was in insurance, more so, but a lot of that is prescribed by regulation. You're just, you're not allowed to discriminate on education or gender or that sort of thing. Well, gender you are, but not discriminate. You have to loss justify, yada, yada. Insurance, good stuff. I don't know so much in the payment space because a lot of it is, how do I put it, a little bit more on like the cutting edge technology to gain components. So does our competitors use things like the pingback rate from the IP address? I don't know if they even have that. I sure don't, but I know PayPal does. I'm trying to get access to those kind of tools. So a lot of it is like evolving feature creation is really driving this kind of like no holds barred technology space. No holds barred, that doesn't sound right. But you have the complete freedom to use whatever you want as long as you're kind of sure that you can get it consistently. Because I'm more concerned about like, are we actually getting the real data? Or am I just like getting fake data or bad data or corrupted data? Yeah. Is there someone else? No, go ahead. All right. So the question is, there we go. There's two sorts of grid searches in scikit-learn's kit. Right now, we can see we're using Gridsearch CV, which is just doing the Cartesian join, as we kind of saw on that graph of like every possible parameter in these parameter lists. The other one is giving it a range. So you wouldn't say C equals and give it a list. You'd give it a range. C is equal from 0.001 to 10 or whatever. And it would just randomly pick values throughout that list, right? Good, because I've used it like 3 times. Is there a reason to use one or the other? The random one is what I use when I'm doing more competition stuff, and you want to kind of narrow down on like the actual more perfect term, because you can get way more value by doing less work. This one is fantastic when I'm playing with a new model. I want to explore these weird corner cases where, oh, everything above this just keeps, hitting 0, like 0, no one's fraud. And you're like, that seems odd. When I'm graphing, I like my regular little dots across the way. Random is just as good. I think it's harder to understand when you're first exploring a new parameter space. But in the end, I think random's probably better. Any other questions? Because now we've just hit our 10 minutes for questions area.
I have a very long question. So part of data science isn't just to choose the best model, it's to understand the data itself, right? So when you choose the parameters, that's part of the process of going in and saying, okay, well, K of 5 here is doing better than K of 10. It tells me about my information space. So how can you use this grid search to sort of understand the data instead of just sort of pick the best model?
So the question is, how can we use the grid search to understand the data as opposed to just popping out kind of that best model? Let's see. So when we do something like this, right, it gets pretty hectic, but graphing the average results by the parameters that went in is pretty helpful because you tend to see trend lines. So I guess I do that. We graph kind of these results, and then I plug in a whole different feature set that maybe the risk team says, actually, we don't use credit score because it's probably stolen identity, so let's just use these things that we know are actually true. And you can kind of compare these results across different models. You end up with just a screen full of graphs, which makes you look really busy if anyone walks by. But I've lost the train of it. How do you basically use grid search to explore your parameters, or not your parameter, your feature space?
Your data, to understand your data.
Yeah, to understand your data. So if, to take your example, if we try k-folds 3, this cross-validation, and we try it with 10, and there is a big difference, I am really going to get in and just start opening up like Pandas data frames to look at it, because there shouldn't be a huge difference between 3 and 10. There should be a slight difference, it's averaging, but if that means like one of the segments of the 3 chose a chunk that was totally non-intuitively part of the rest of the data, then we might have some sort of outliers that are really throwing things off, or consistently null data, that sort of thing. I don't probably use, model tuning per se to really explore the data as much as I have other tools further up the process that we're really using to look at it.
I don't know how many years you're already doing this kind
Yeah, the question is how robust are patterns over time? So did suddenly fraudsters develop a new trend recently that we've caught and started modeling on? Not so much in the payment space that I've seen. In the insurance space, a little bit more, and that's with like shifting towards more of the what are those things called? The things that plug into your car and record stats. Yeah, those things. Can't remember their name. Huh? Smart Drive? Anyone? No? All right. I think those are planes. So yeah, I haven't seen that. We tend to test for it. So a lot of times when we're first collecting variables, we will just do a straight up like, give me the variable counts by week or by month. And you do see things. And suddenly you see huge things. And you're like, oh, that's when we changed in our system from like taking write in, where you just wrote in what your industry was, to like select from a drop down. And there were like 50 types of industries, and now there's like 6. And maybe I should like account for that when I'm maybe doing a mapping. But that's definitely further up in the process. I mean, time is often plugged into the model as a parameter, and we look at kind of its effects. But I don't see that changing as much as you think with fraud. But then again, you know, good cutting-edge fraudsters have a really low frequency and a really high severity, as opposed to your average fraudsters that are just bad at business and don't send product out. And those are much easier to catch. Fraud is actually a really confusing space when you get into modeling. Yeah.
So if you have an expensive model to evaluate and you're doing a large good search, that seems very suboptimal when there's that you can evaluate your model less often.
The question is, if you have a very expensive, I'm assuming time and data size to evaluate, are there other methods to use to, I guess, tune your parameters? I mean, in my experience, I end up just subsampling down. And then you can, there are a lot of tools out there like the AWS stuff where you just spin up as many cores as you want. And you pay your 30 cents and suddenly it's all done. Which is pretty neat because it records all of your data and it records your fit model, which I keep coming back to because I find it super convenient that you don't have to like refit the model one last time when you know what you want. So no, I actually don't tend to use other methods when I'm doing this parameter exploration as much. There are. Read the, yeah. A little Googling will get you a lot. Yeah. Good question. Question is, how long do we spend tuning parameters, and what's the benefit in terms of accuracy or what have you? It is a good question. It has always kind of changed on a case-by-case, project-by-project basis. A lot of it is I have like some good models that I like and trust, and I want to see some new techniques on them. And so I have a nice like baseline comparison. And then you get maybe a little bit, maybe a ton. Maybe you play with an assemblage that picks up, because a lot of times what you get in modeling is like model 1 picks up like 90% of the signal, and model 2 picks up this little bit over here and shares some, and you just like average these models and you get a much better model overall. And then that's one like, am I caring about are you a fraudster or not, or am I caring about catching like the really hardcore fraudsters that cost us the most money? Because one model maybe does much better at that, and averaging the two gets us a ton of value, but maybe not a ton more fraudsters caught. So project by project, it varies quite a bit. Yeah. I think it also, so I guess the other thing this brings me to is there are a lot of papers, there's a lot of blog posts written on what models are good for what sorts of data sets, and I don't ever like trust that. It sounds like a great suggestion, and it's very easy to just try it out, which is I think really the point I'm trying to get across on this talk, is that there are tools like this that make this sort of thing, which is complicated and wordy and full of jargon, pretty easy to just start experimenting with and hacking away with, which is what I really recommend kind of getting used to, because you will find that there are a couple that tend to converge and are the best. But there's no reason to like know what the best is. You should just try new things. Yeah? Any other questions? Yeah. So the question is, how do we keep a model accurate over time after we've deployed it? And that's not my talk. But that is part of model validation. So you can do some straight up A/B testing. You can hold out a small subsample as a core control. You can rescore your model and see how much it changes. You could do it daily or hourly if you wanted to. But that leads to, well, there's different proponents on that one. I think it leads to overfitting because I don't think people change that much. But in the right world, like high frequency trading, clearly you'd want to care more about like more local shifts. So I like holding out a little bit of a control sample, see how they do compared, see if they actually match. Because so if we use this model 100% to predict fraudsters, and we said, okay, great, how many fraudsters did we miss? Well, that's too bad. That counts against it. But how many did we catch using the model? There gets to be a bit of, you guys familiar with confusion matrix, like true positives, all that? There gets to be a little bit of an overfit where you actually are not able to test to see if people would have been fraudsters because you've already shut them down for predicting they're fraudsters. So that's why you'd want like a holdout control set, even though maybe that means you are guaranteed to let through more fraudsters than you would otherwise. And that's a little bit of a business decision, a little bit of an argument with upper ups. You, yeah, keep the science pure or maybe just make more money. I don't know. Cool. Thank you, everyone, for asking so many questions.